Hello everybody and welcome to our webinar. Today's topic is simulation of the building thermal insulation with QuickField. My name is Vladimir, I am Director of Marketing Support, and after my short introduction, my colleague Alex will continue with QuickField examples, and as usual it will be live demonstration. Let me start from the brief overview of QuickField analysis capabilities. This slide shows the set of QuickField types of analysis. They may be grouped into electric suite, magnetic suite, and thermostructural suite. Also, it should be mentioned that many types of analysis may be combined, as it is shown on this slide, and this makes QuickField a powerful tool for multiphysical analysis. Important feature of QuickField is that in addition to the graphical user interface, it has application programming interface, and it is possible to organize interaction between QuickField core functions and external applications like Microsoft Office, MATLAB, or many other programs. The building industry has a long history of powerful software tools for structural and thermal analysis, but growing attention to the ecology, stricter energy efficiency rules, and increased requirements for computer simulations in the building standards demand simple and flexible tools, which may be used occasionally by practical engineers who do not have much of experience with simulations. For these applications, simplicity and user-friendliness of QuickField make it a tool of choice. From the large selection of QuickField analysis possibilities specifically for thermal analysis, building insulation requires using other thermal analysis models. And to validate QuickField against the ISO 177-2 standard, which is thermal performance of windows, doors, and shutters, we prepared a Microsoft Excel document which includes macros which interact with QuickField models for calculating air gap thermal conductivities according to the ISO recommendations. This is a convenient practical tool which may also be used as an example of application of our active field technology. What is important, what all these features are made with usual difference between QuickField and other packages, because QuickField is a unique tool which requires no training. And now my colleague Alex will prove this statement with his live demonstrations. Alex, please continue.
Hello. Today on this webinar we will review 6 examples. 2 verification examples that are included in ISO standard tests, and 4 showcases related to different aspects of building thermal insulation. These are windows insulation, balcony insulation, the roof insulation, and the foundation insulation. The first example is the verification example against the ISO standard thermal bridges in building construction. This example represents the concrete slab laid on the steel frame, and the frame and the slab are in contact through the insulating plate. So this is some kind of the roof element. The bottom surface is in contact with the warm air inside the building, and the air temperature is 20 degrees Celsius, and the top surface is in contact with the cold air with the temperature of 0 degrees Celsius, and the surface thermal resistance is specified. Now, as this is not the solid to solid contact, but this is the solid to the gas contact. There is specific thermal conducting resistance. So this is the value of the thermal conducting resistance. The dimensions specified here are in millimeters. It is the static heat transfer problem, and the thermal conductivities of the concrete, of the insulation, of the air, and of the steel are specified. Our task is to calculate the temperature distribution and compare the temperature value in reference points. The reference points specified in the ISO standard are all the corners. So here, here, in this corner, in this corner. The geometry model features vertical symmetry, so only the right half is simulated. And on the axis of the symmetry, we will set the zero heat flux boundary condition. Now I will start QuickField. I will create the new problem. This is the problem name, and this is the location folder. As I said, this is the steady-state heat transfer problem. Now here you should draw the geometry model, or you can input the geometry model from the CAD drawing. I already have the CAD drawing prepared. Here it is. Now this is the geometry model. Here I should assign labels to every geometric object. Now what I have here. This is the concrete. This is the metal. This is the insulation. And this is the air. The bottom surface is warm air, and the top surface is the cold air. And this is the axis, the vertical axis. Now I have the geometry model labeled. So for each object there is the label here in the tree. And next step is to assign physical properties for each label. Now let's check. For the concrete I should specify 1.15, and for the insulation 0.12. Concrete 1.50. This is the static problem, so I do not specify the specific heat, nor I do not specify the mass density. And for the insulation, 0.12. For the air, I specify 0.029, and for the metal, I specify 230. Next, I should assign boundary condition. So as I said, at the vertical axis, I have 0 heat flux. The warm air. This surface is in contact with the air, so I should specify the convection coefficient. The temperature is 20 degrees and the convection coefficient is reciprocal to this value. So I type this value. Now for the cold air, again I specify the convection. The temperature is 0 degrees Celsius and the convection coefficient is reciprocal to this value. Now everything is ready. I can build the mesh, save all problem files and run the simulation. And here you can see the temperature distribution. You can adjust the field picture. I will switch off the color map and switch on the isotherms plot. To calculate the heat flux, you should build the integration contour. You should use the contour tool and select the top or the bottom edge. Here you can see the contour is built, and then you follow to the integral calculator and calculate the flux. And to calculate the local values, you should use the local value calculator. So this is the temperature at this point. I can manually adjust the point coordinates. Now this is the temperature. And this is the overall heat flux. Now let's compare these values with the reference values. Here you can see that the heat flux should be 9.5. If we compare the difference, in QuickField I have 9.5. 116 divided by 9.5 is 1/10 of the percent. The difference in the flux value is only 1/10 of the percent. Now let's compare the temperature value. In QuickField I have 16.335 and in reference I have, now this is the reference and this is the point J. There is no reference temperature for the J point, so let's choose another point, for example D. I will click here and adjust the coordinates. Now it should be, yes, 6.2028. In a reference I have 6.3. Now let's compare the temperature at other reference points. For example, A, C, F. Let's zoom in and try again. Seven 7.1. That's the point C. 7.90. 7.9. Now let's check the point F. It should be 16.4, and in QuickField I have 16.4. In order to pass the test, the difference between the measured value of the temperature and the reference value of the temperature should be less than 0.1 Kelvin. And the difference between the measured heat flux and the reference heat flux value should be less than 2%. So you can see that QuickField passes this test. And we move to the next example. This is the next example, verification example against the ISO standard thermal performance of windows, doors, and shutters. There are about 10 two-dimensional test cases presented in this standard, and we will consider only one of them. It is the aluminum-clad wood frame section with the calibration insulation panel instead of the glass. Blue blocks are made of aluminum. Orange blocks are made of wood. This is the insulation panel, the calibration insulation panel. And this is the insulation, the resin. Temperature at the outside is 0 degrees Celsius and the temperature at the inside is 20 degrees Celsius. Our task is to calculate the heat flux and the two-dimensional thermal conductance. The two-dimensional thermal conductance is calculated from the total heat flux per length. This is the length, divided by the temperature difference between both adjacent environments. So in our case, the temperature difference is 20 degrees, and we should measure the flux. The main challenge here is to take into account convection and radiation heat exchange that present inside the air cavities. Some cavities you can see are closed and some cavities are slightly ventilated. The ISO standard recommends to adjust the thermal conductivity of the air so that the conductive flux will also include the radiation and the convection heat flux components. The procedure is described in details in the standard. It is essential that the convection flux is in direct proportion to the temperature difference and the radiation flux is in direct proportion to the fourth power of the temperature difference. So to find the effective thermal conductivity, we need to know the temperature difference. And to find the temperature difference, we need to simulate the problem. So this is the iterative task. First, we simulate the problem with some predefined value of the thermal conductivity of the air thermal conductivity. Then we find the temperature difference for each cavity. And we calculate the effective thermal conductivity for each cavity from the temperature difference. And then we run the simulation again and repeat the simulations until the process converges. I will create the new problem in QuickField. Specify the problem name and the location folder. The problem type is again steady state heat transfer. Here you should draw the geometry model, or you can import the geometry model from the DXF format. This is the geometry model. In the geometry model, you should assign label for each object. I hold the Ctrl button pressed to select multiple objects. This is the wood. This is the panel. Again, I hold the Ctrl button to unselect objects. This is the aluminum. And this is the rubber. And I have the air cavities. As I should calculate the effective thermal conductivity for each cavity, I specify different labels for each cavity. This is the air 1, This is the air 2. This is the air 3. This is the air 4. This is the air 5. This is the air 6. Those are non-ventilated cavities. And I have the slightly ventilated cavity, and I give it the label air ventilated. Now let's check. Air 1, air 2, air 3, 4, 5, 6, air ventilated, aluminum, panel, rubber, and wood. Next I should assign label to boundaries. The top boundary is the warm air contact surface. In fact, there is the different thermal resistance, the different convection coefficient at the horizontal and the vertical surfaces, so I should give this label air horizontal, and this is air vertical. And the same for the cold surface. This is air cold horizontal, and this is the air cold vertical. For the air, I specify the thermal conductivity of the air. As I do not know the temperature difference, I specify the thermal conductivity of the motionless air. And I repeat this for every air block. For the aluminum, I specify the thermal conductivity of the aluminum, 160. For the panel, I specify the thermal conductivity of the panel, 0.035, and for the wood 0.13, and for the rubber 0.25. For the rubber 0.25, and for the wood 0.13. Next, I should assign physical properties to boundary condition. This is the convection surface, and I should specify the air temperature and the convection coefficient. The convection coefficient is a reciprocal value to this thermal resistance. So I type this value here. At the vertical surface, I have the same temperature, but the convection coefficient is slightly different. Now at the horizontal surface, I have the 0 Celsius degrees temperature, and the convection coefficient is the reciprocal value to 0.04. And for the vertical 0.04. Now I have the geometry model and the material properties ready. I can build the mesh, save all problem files, and run the simulation. Now I get the temperature distribution. I can adjust the field picture. I will switch off the color map and switch on the isotherms. To measure the heat flux, I should build the integration contour. I simply select the top surface, and this is the heat flux. Now, as I know the temperature distribution and I know the temperature difference, I can adjust the thermal conductivity of the air cavities. The procedure is described in the ISO standard. And we automated the task by using Microsoft Excel. So from our website, in the support, in the downloads free tools, you can find the equivalent air cavity thermal conductivity calculator, which includes the Microsoft Excel. Now I will show you how to use it. On this sheet you should specify the block labels, where you should calculate the thermal conductivity. In our case, these are these labels and air ventilated. So I type here air 1, air 6 and air ventilated. Next you should specify which cavity is isolated or slightly ventilated. Air 1 through 6 are insulated and this cavity is slightly ventilated. Next you should specify the initial value of the thermal conductivity, which is for the air is 0.035. Now, following the procedure described in the ISO and taking into account the convective heat transfer and the radiative heat transfer, the effective thermal conductivity coefficient is calculated for each cavity, and the results are presented here in the table. And this is the step 1 results, and this is the difference in percent between the initial and the calculated thermal conductivity. Now let's make the next step. and I will show you the QuickField. You see the QuickField is operated through from the Excel document. And again, for each cavity, the thermal conductivity is calculated. Now let's make 2 more steps. And 1 more step. You can see the ports are almost converged. The difference between 2 steps is less than 1%. Now for this last result, let's find the heat flux. Again, I will switch off the color map so you can see better how the contour is built. This is the contour tool. I select the integration contour and calculate the heat flux. So this is the heat flux. Now let's calculate the thermal conductance as it is described in the ISO standard. I should divide the heat flux by the temperature difference. The heat flux is 5.38, 5.3798 divided by the 20. It's 0.269, and the reference value is 0.263. The difference should be less than 30%. Now let's calculate the difference. Divide by 0.263. The difference is indeed less than 30%. So we pass this test. We have simulated 2 verification examples, and now we move to the showcases. The first showcase is related to the calculation of the heat losses through the window. The model includes the window's frame, the glass, and part of the wall. 2 types of the wall are studied: the old style wall made of brick and the modern composite wall made of aerated concrete, rock wall insulation, and the plaster. The air temperature outside the building is minus 32 degrees Celsius, and the air to wall thermal resistance is 0.033. The air temperature inside the building is plus 20 degrees Celsius, and the air to wall surface resistance is 0.11. Our task is to calculate the heat loss through the window and compare the results. Now let's start QuickField and simulate both cases. Here is QuickField. I create the new problem. Windows. Now the problem type is steady state heat transfer. This is the geometry model editor, and here I should draw the geometry model. Or I can import the geometry model from the DXF format. To compare the results, I will simulate both types of the wall in the single model. So here is the modern style wall, and now I will import the old style wall. Here it is. In the geometry model, I should label all the geometric objects. Now this is the brick. This is the wood. And this is the glass. I hold the console button to select multiple objects. And I have the glass in this window. As I already have the glass label, I do not type the label name here, but I choose from the already selected labels. Now this is the air 1. This is the air 2. From the previous examples, you know that the air thermal conductivity should be adjusted to take into account the convective and radiative heat exchange. So essentially I have two different thermal conductivity for the air gap 1 and for the air gap 2. So I have two air gaps. Now this is the aerated concrete. This is the insulation. And this is the insulation too. Now let's check the model. Air 1, air 2, brick, wood, glass, insulation, aerated concrete. This is wood, and this is the cement. Now it seems I have all objects, all the blocks labeled, and I should now label the boundaries. This is the internal boundary. That has the temperature of 20 degrees Celsius. And the same in the old style wall. This is the internal boundary. and I give it the same level, 20 degrees Celsius. And this is the external, the cold side. It's 32 degrees Celsius. And the same for the second wall. This is the cold side. Now, next step is to assign physical properties for each geometric object. For the glass, I should specify the thermal conductivity. .76. For the brick, I should specify the thermal conductivity 0.81, 0.93. For the aerated concrete, I should specify thermal conductivity 0.15. For the wood, the thermal conductivity is 0.18. For the insulation, 0.048. And for the first air gap, I already have the effective conductivity that takes into account the heat transfer, the convective heat transfer, and the radiative heat transfer. And for the second air gap, now the external surface, essentially this is the convection boundary condition, and the temperature is -2 degrees, and the convection coefficient is reciprocal to this value, to the thermal resistance. So I type here for the internal surface, it's again the convection boundary condition. I specify the air temperature and the reciprocal value of the thermal resistance. Now you should build the finite element mesh, save all the simulation files, and run the simulation. It seems we forget to label this block. And here you can see the temperature distribution. On the left is the modern style composite wall, and on the right is the old style wall made of brick. You can adjust the field picture, and I will switch off the color map and switch on the isotherms. Now let's calculate the heat flux. I will use the contour tool to build the integration contour. Now I click one edge after another. And this way I build the integration contour. Now this is the heat flux for the modern composite wall. Let's remember this value. This is, I will copy the value, about 38 watts per meter of length. Now let's build another integration contour. I select the external surface of the old style brick wall. And the heat flux is about 68 watts per meter. You see, there is indeed the big difference in the thermal insulation properties of these two walls. And we move to the next example. This is the balcony slab simulation case. You see, the wall is made of the brick and insulated with a rock wool insulation. But the balcony slab breached the insulation, so there is the cold breach here. Our task is to calculate the heat losses for this cold breach. All dimensions are in millimeters. The air outside has the temperature of minus 32 degrees Celsius, and the air to wall thermal resistance is 0.033. The air inside the building has the temperature of 20 degrees Celsius, and the air to the wall thermal resistance is 0.11. Now let's start QuickField and simulate this case. I will create the new problem. The problem name is balcony. The problem type is steady state heat transfer. This is the geometry model editor window, and here I should draw the geometry model. Or I can import the geometry model from the .xf file. This is the geometry model. Here I should assign physical properties for each element. This is the brick. I hold the control button pressed so to select multiple objects. And this is the brick. And this is the concrete. This is the rock wool insulation. And here I have the plaster. and this is the steel. Now I should assign label to the boundaries. This is the warm side, temperature plus 20, and this is the cold side. Temperature minus 32. Now I should specify physical properties for each object. The brick thermal conductivity is 0.87 and the concrete thermal conductivity is 2.04. Brick 0.87, concrete 2.04. The steel has conductivity of 58 and the plaster has conductivity of 0.93. Steel 58, plaster 0.93. And for the rock wool, I have the thermal conductivity of 0.041. 0.041. Now, at the internal, at the warm side, I have the convection boundary condition. I specify the temperature of the air and the convection coefficient. The convection coefficient is reciprocal to the thermal resistance value. So I type here 1 divided by the thermal resistance. At the external side, I specify the air temperature minus 32 degrees and the convection coefficient, which is reciprocal to this thermal resistance value. Now I should build the finite element mesh, save all problem files and run the simulation. Here is the temperature distribution. You can adjust the field picture and switch on, for example, the heat flux vectors. And again, I will adjust the field picture. You see, indeed, there is the cold breach here. Now let's calculate the overall heat losses. To calculate the losses, you should build the integration contour. Essentially, all the heat flux comes from the warm side to the cold side. So you can simply build the integration contour somewhere here inside, between the warm and cold side, and calculate all the heat flux that cross this contour. So the heat flux from the warm to the cold side is 55 watts per meter of model length in Z direction. Now let's move to the next example. In this case, we will simulate the flat roof to the wall abutment. You saw in the previous case that there was the called bridge when the balcony slab bridges the wall. And here there is the cold bridge because of the roof railing. To eliminate the bridge, it is advised to use the foam cement instead of the brick in this place. Now the roof has the composite construction. It consists of the ceiling slab, insulation, foam, plaster and waterproofing layer. The temperature inside is 20 degrees Celsius and the air to wall, air to roof thermal resistance is 0.11. The air outside has the temperature of minus 32 degrees Celsius and the air to the wall and to the roof thermal resistance is 0.033. Our task is to calculate the heat losses and compare the heat losses in case of the brick wall and of the brick wall with eliminated cold bridge. Now let's start QuickField. I will create the new problem, roof. The problem type is steady state heat transfer. Now this is the geometry model editor window, and here I should draw the geometry model. Or I can import the model from the .xf file. To compare the results, I will duplicate this model, and instead of the foam cement there will be solid brick wall here. So that's the difference between these two models. Here I have the foam cement and here I have the solid brick wall. Now in the geometry model I should assign labels for each geometric object. So this is the brick. This is the slab. This is the insulation. This is the polyurethane foam. This is the plaster. And this is the waterproofing layer. Now let's check it. Brick, insulation, plaster. Oh, this is not the plaster, this is the polyurethane foam slab and the waterproofing layer. And this is the foam cement. Next, you should assign labels to the boundaries. These and these. These are the cold side. Hold on the control button pressed to select multiple objects. So this is the cold side. Temperature minus 32 degrees. And this is the warm side. Plus 20 degrees Celsius. Now I should specify physical properties for each object. For the brick, I specified thermal conductivity of 0.9, and for the plaster I specified the same thermal conductivity. For the concrete, I specify the thermal conductivity of 2. For the foam cement, I specify the thermal conductivity of 0.15. For the foam, I specify thermal conductivity 0.045, and the same for the insulation. And the waterproofing have thermal conductivity of 0.17. Now for the warm side, and this is essentially the convection boundary condition, so I should specify the air temperature and the convection coefficient. The convection coefficient is reciprocal to the thermal resistance, so I simply type here 1 divided by 0.11. And for the cold side, I specify the temperature of the air and the convection coefficient, which is reciprocal to this thermal resistance, 0.033. Now I can build the finite element mesh, save all problem files, and run the simulation. And here you can see the temperature distribution. On the right is the wall, the solid brick wall, and on the left is the wall with the foam concrete. Now let's check the heat fluxes. To calculate the heat flux, I should build the integration contour. Essentially, all the flux come from the warm side to the cold side, so I can build the integration contour on the warm side. Now let's calculate the heat flux. It's 36 watts per meter of the model depth. This is the solid brick wall. Now I will clear the contour and build the new one for the wall. We've eliminated a cold bridge, and the heat flux is 26.5. So indeed, using the foam cement blocks, I managed to reduce the heat losses through the cold bridge. And we move to the next example. This is the last case for today. It is related to the calculation of the shallow foundation thermal resistance. The foundation consists of the concrete foundation slab, and this slab is usually insulated by the plate from the ground. Also, there is the 9H cable placed here and here. Our task is to calculate the thermal conductance. In this case, we do not simulate the walls, we do not simulate the roof of the building, we only simulate the heat losses and the thermal conductance through the foundation. Inside the building, the air temperature is 20 degrees Celsius, and outside the building, the air temperature is minus 32 degrees Celsius. Now let's start QuickField and simulate this case. I will create a new problem. The problem type is steady state heat transfer. Here is the geometry model editor window. I can draw the geometry model here, or I can import the model from the .exe file. So this is the geometry model. In this geometry model, I should also add the earth. So I will correct this drawing and add the earth block. Now this is the geometry model. In the geometry model, I should assign labels for each object. This is the ground. This is the concrete. This is the gravel. And these are the thermal insulation plate. Next, I should assign labels to the boundaries. Inside the building, I have somewhere the wall here, so that is the floor surface. plus 20 degrees. And outside the temperature is minus 22 degrees. It's minus 32 degrees. Now I should specify physical properties for each object. For the ground, the thermal conductivity 0.36. For the concrete, the thermal conductivity is 1. For the gravel, the thermal conductivity is 0.36. And for the insulation plate, the thermal conductivity is 0.031. The floor is in contact with the air, so I should specify the convection boundary condition. The air temperature is 20 degrees and the convection coefficient is reciprocal to the thermal resistance value. For the outside, I specify again the convection temperature, the air temperature minus 32 degrees, and the convection coefficient, which is reciprocal to the thermal resistance value. Now I can build the finite element mesh and run the simulation. And here you can see the temperature distribution. You can adjust the field picture and switch on, for example, the heat flux vector plot. And I adjust the vector plot. So this is the way of the heat flux. And to measure the heat losses, you should build the integration contour. You can build the integration contour on the warm side or on the cold side. I will build the contour here on the warm side. I simply click in the edge and you can see this is the integration contour. Now I can calculate the heat flux. And if I divide the heat flux by the temperature difference, I will find the thermal conductance of my foundation.